Good morning, everyone. My name is Luis Camilo Suescun, President of IAH Colombian Chapter, and I want to welcome you to our third cycle of groundwater talks. We really appreciate your support to our chapter and join us with our volunteer activities. I would like to share with you the following.
Sorry?
Yes, sorry, excuse me for the interruption. I would like to share with you the following link where you will find our talks schedule. Here are some general rules for our session. We have maximum 1 hour of live presentation. If you have questions, please feel free to write those on the chat. At the end, the speaker will have 10 minutes to answer maximum 10 questions of this. Also, we appreciate that at the end of the talk, you fill our survey that will help you to improve our talks and will collect all your impressions. Now it's time to introduce to our first speaker. Dr. Daniela Ducci, she has full professor at the Department of Civil Architectural and Environmental Engineering GIS of the University of Napoli Federico II, reviewer of an expert evaluator of Italian and international research projects, president of the Italian chapter of the International Association of Hydrogeologists. Her research activity takes place in the field of hydrogeology and more precisely in the qualitative and quantitative protection of groundwater resource. Also, in relation to the impact of climate change, author of numerous scientific papers published in the international index journals. She is associate editor of Elion Elsevier. It has scientific collaboration with Italian and foreign institutions as Portugal, Argentina, UNESCO, and in context of research projects. We are grateful for your connection. Enjoy the webinar and thanks for sitting with us.
Thank you very much, Camilo. Please could you unmute me? Okay. Thank you very much, Camilo. And I am Daniela Ducci, and I'm very glad to be here now with you. And this is to kick off the third edition of this groundwater talks, a very interesting initiative of the Colombian chapter. And this is also my presentation, a tribute to my friend Luis Ribeiro from Portugal, who died a few weeks ago. And he was a very friend of all the world of Colombian hydrogeologists. Thank you for that. And I will begin with my presentation. I don't see my presentation now. Please, Camilo.
Can you share your screen, please, Daniela?
Okay.
Thank you.
Okay, thank you. My presentation, this is the title of my presentation that Camilo introduced me. And okay, water. Everybody knows this partition of water in the world. And groundwater is few, but it's very important part of water in the world. Is more than water in rivers and lakes. And water depends on the hydrological cycle. Everybody knows the hydrological cycle and is affected by the cycle of precipitation and evaporation. And the infiltration is the main part that produces groundwater. Climate change is a very big problem. It's a very big problem for not only for nature, but for agriculture forests, coastal areas, and marine resources, but especially for water, surface water and groundwater. This is the topic of today. How climate change affect groundwater resources? In two ways, as direct effects with the lowering of groundwater levels and decrease in spring flow discharge, and other effects that can be classified as induced effects, because the lowering of levels can invert the flow, attracting other water from the river, or that can be polluted, or in coastal areas can favor the advance of marine water intrusion. Moreover, you have also a cascade effect with an additional groundwater depletion due to the increase in water demand and then in groundwater exploitation. This is resuming the problem of climate change, and which is the part affected. Precipitation is affected by climate change, but especially evaporation. Evaporation due to changes, the increase in temperature. This is the scheme of my presentation, and the first part is a very basic, it's quite basic part of assessment of hydrogeological balance, but it is important because some parts that we give as normal, as very easy, are not so easy, because hydrogeological balance is something very important, and they require a lot of careful operation. This is the assessment of hydrological balance. This is the same, the hydrological cycle. In undisturbed situation, the hydrological balance is precipitation, actual evapotranspiration or effective evapotranspiration, and runoff, surface runoff, and the differences from the precipitation is the infiltration, and this constitutes the recharge of groundwater. Precipitation is very easy to calculate. You have to see that because we have a lot of meteorological stations. And now rain gauges are very very well designed. They can measure the amount of precipitation, and also you have a transmission of data nowadays, transmission of data, and you can read and know this data in remote from your computer. You can know directly this data. For example, this is the monitoring network of rain gauge of climatic or weather stations of my region, and you can go to this station and you can know the temperature, the precipitation, and in real time. This is very good. This is fine. But precipitation data are point data. You are working in an area or in a basin, and how you elaborate precipitation data? Well, you have a lot of methods. The easier is the average precipitation rate. This method is quite valid where in small areas with not morphological complicated, for example, in flat areas. For example, this is the sample with the values with the few differences between one each other, and this is a good method. But at regional scale, you generally use isoyates, curves of the same precipitation. This is my region, Naples is here, my town. And you have quite differences. This is a coastal area with the same values. They are yearly data, and this is about 900 millimeter for years of precipitation. And this is a good method at regional scale. Or distant polygons. This is a method, a little bit an old method. The territory is divided in polygons, and each polygon has a station in the interior. And this is all the polygon as the value of precipitation of the station that it includes. This is an old method. The calculation is with median for each from one station to another, and after you can construct these polygons. Well, this is for me not a good method, because you can have big differences from a polygon to another, and then this I think the plane is a continuous variable, not and then you have in this position as similar a wall of water. For example, this station is 1000 millimeters per year, and this other station is 1500 and 500. And then you have a lot of differences between this polygon and this other polygon. But this is a method. Another method is when you have a good relationship between precipitation and elevation, and you can calculate precipitation from the digital elevation model, from the elevation of the area. For example, this is a very good correlation between precipitation and elevation in meters above sea level. In this case, you can use this law, for example, this law, to transformate the digital elevation model in a raster model, digital elevation model in a precipitation model. This is very easy, but the relationship between precipitation and elevation is not always good. This is, for example, a case of the Sorrentine Peninsula, south of Naples, and you can see two different laws or more, and then this is not so easily applicable. Just a moment, this is a southern part, and this is a northern part of the peninsula. Why that? Because the yearly mean precipitation depends on the elevation, but also depends from the distance from sea, lakes, and is very sensible to the distance from the main ridges. Very important in southern Italy, for example, is the Apennines watershed. Wow, because the water divide separate the western part, where you have the Atlantic, the provenience of the Atlantic storms with the rain, and the other part where we have no influence of this precipitation. And then you have the Tyrrhenic side with the high precipitation, and the Adriatic side with very low precipitation. Slope aspect also is important, because northern side are generally more rainy than other. Presence of humid area or wetlands. Other factors are important, affects the single rainfall event, as atmospheric pressure, air temperature, soil humidity, etc. Then precipitation. That seemed very easy to calculate, because you have the value and instruments to very easy instrument to measure that. It's not so easy to have a distribution of this precipitation at aerial level. And the other, well, now the actual reflective evapotranspiration. This parameter is very difficult to calculate. This is two parts, evaporation and the transpiration from the plants. The evaporation in air depends on solar radiation, air and water temperature, wind velocity and turbulence, atmospheric pressure, water salinity, soil humidity. The part of transpiration depends on vegetal species, but not only the type, the age, the development, the root depth, the number of leaf stomas, and then is a very difficult to calculate this parameter. What about direct measurements? You have some instruments as evapotranspirometer and lysimeter, like this of this picture, but are very expensive and difficult to maintain. The maintenance of these instruments are very difficult because you have problems. This is coarse grain, but you have sure that this sand can go to this and after to this, and then you have to clean. This is a part that you can access to clean this part for this. And then what? Moreover, the validity is only local because it's very linked to the, for example, to the land use in this part. And then you have formulas, empirical formulas. We have a lot of empirical formulas, Thorne formulas, Perman equation, Turk's formula to evaluate the potential evapotranspiration, which is the evapotranspiration if you have all rain available, but generally the actual evapotranspiration is less than potential evapotranspiration. There are also formulas for directly calculate the actual evapotranspiration. Also, you can estimate evapotranspiration from satellite data. You have a lot of situations. Generally, it's better to use something very easy. Depends on, the, for example, an empirical formula, very easy, is the Turk formula for the actual evapotranspiration that you use in southern Italy, in the Mediterranean basin. And because I have a lot of tests with this formula that demonstrate that this formulation is quite good for this area. And it's only this formula depending on precipitation and temperature. This is good because temperature is always linked to the elevation. You have an inversal correspondence between elevation and temperature with very high correlation. You can see in this picture. And this is for the whole region of Campania, my region in southern Italy, with the maximum temperature and minimum temperature. You can see very high correlation coefficient for this between temperature and elevation. And then from temperature to use after in this formulation of Turk, you can do this calculation that you have explained before. This for each pixel in a raster model, you can correspond a value of temperature. And this is the variation in temperature. This is the law. This universal law, you can see all this. This is easy, but the formulation, the result is the result, good. And now you have the precipitation and the actual evapotranspiration, and you calculate this. This is the total flow. The total flow is the sum of the surface runoff and the infiltration. How we can calculate the runoff and the infiltration? The runoff can be calculated by direct measurement with the measure of at the end of the main rivers. We can calculate the flow rates, but the hydrographic basin coincide with the hydrological basin? Almost never. It's very difficult that you have this coincidence. generally are different because the hydrographic basin is something impervious, not so permeable, while hydrogeological basin is in part more permeable, and that's you have not coincidence between this. And then we must calculate, for example, the water that from surface water of another basin, which can began to is now groundwater of this basin for underground flow, and it's very difficult. The solution, generally runoff, is also calculated indirectly. Runoff depends on the outcropping hydrogeological units, slope morphology. Generally flat areas, the runoff is very low and limited to agricultural channel, for example, or soil type and land use in terms of vegetation, crops, or urban areas are very important because in urban areas, the infiltration is very low because you have surface not permeable, asphalted surfaces. And the typical is to use a Richard coefficient based on the permeability of the outcropping rocks. It's very easy, it's not so precise, but this is percentage of the total flow that represent the infiltration. This is different in limestone, is very high, and lava is very high for fracturation, and in sand for porosity, and of course debris is very high, etc., etc. In clay rocks or metamorphic rocks is very low. And then this is a resume of this operation that you have explained. This is precipitation, temperature. You can calculate, for example, using the actual evapotranspiration. The differences between precipitation and evapotranspiration will give the flow, which is the sum of runoff and infiltration. Using a lithology map, you can transformate this map in a Richard coefficient map and to have the recharge and the surface runoff divided. But what? The uncertainty of this calculation is brief. Hydrogeological balance are very useful and powerful, but only to indicate an order of magnitude of these parameters, of these factors, because you are not sure. Only in the point of the precipitation you are sure of this value, but you have also in precipitation and uncertainty is difficult to calculate, but the order of magnitude is very important to have this idea, this range of idea. Moreover, you have a situation, you have now calculate, I show you only an unperturbed situation, very easy, but the real world is different. You have also runoff from other groundwater bodies, or infiltration, or you have a relationship with aquifer located below, or you have some anthropogenic artificial recharge or exploitation. Then you have to calculate a lot of parameters, generally. The hydrological balance only are important to have an order of magnitude. This is very important, but this is an important indication. This is an example, a very easy example of balance. This is in Germany. You can see the precipitation in less than in Italy is, in this case, 800 millimeters per year. The evapotranspiration is quite low with respect to Italy because the temperature are not so high. And you have almost 200 millimeters of groundwater recharge. And some less of surface runoff. And you can compare this situation with this situation in Namibia. The precipitation is a term that's in German, but the evapotranspiration is almost the same of the precipitation. And then groundwater recharge is very few. It's only 3 millimeters per year. This is the sense of the balance calculation. 12 differences. Now, this is my basic introduction, but I think it is important to focus on the problem. And now I explain this GIS-based procedure named Big Bang 1.0 for the hydrogeological balance of Italy. I introduce Italy. Italy is located in southern Europe with a surface of 300,000 square kilometers and about 60 million of inhabitants. The climate is temperate Mediterranean and generally humid, but there are also some semi-arid areas in the southern part of Italy and in the island with temperature higher and less precipitation. But the normal range in Italy is this. And from the hydrogeological point of view, you have some impermeable, not permeable rocks with permeability from low to very low, and small springs in the Alps, where you have metamorphic and plutonic rocks in Sardinia and in Calabria. And you have very important karstic areas with very big springs in the central part of the Apennines, this in light blue. And you have alluvial units. The most important is the Po plain, but you also have a coastal plain in this Tyrrhenian part with important aquifers. And finally, volcanic units, this region, or in Lazio, in Campania region, Lazio region, and also in Sicily. In Italy, groundwater is very important. Use a lot of groundwater. The 85% of the water demand is satisfied by groundwater, and also covers agricultural and industrial needs. Use groundwater for every kind of water demands. National groundwater resource is annually renewed for more than 50 billion cubic meters. Is a lot. For imagine this quantity, this is more than the total amount of the water stored in the Lake Garda. Lake Garda is in northern Italy. This is a very big lake. You can see here the dimension is very vast and very deep, this lake. And to have an idea, this is the renovation of groundwater resource each year. This Big Bang is proposed by the Italian National Institute for Environmental Protection and Research that developed this procedure. For evaluating all the factors of the balance at national scale on monthly basis. And you have explained this program, this procedure, in a paper presented at the Congress in Granada. This is the Congress in 2017, and this paper explains the functioning this method that I now explain to you. This is the Big Bang computational scheme. This is an automatic procedure in a GIS environment and is based, this is very important, on available and easily accessible data, also from the web. We use the web resources, the hydrogeological data published as web resources for this program. and it's based on a special distributed model with 1 kilometer resolution grid. This is, for example, this is a dimension of 10 kilometer resolution grid is in red, and this in gray is a resolution grid of 100 kilometers. This is important because you can aggregate data from 1 kilometers to a grid of 10 kilometers over 100 kilometers. You can observe at a different scale with a minimum of 1 kilometers. The model is very simple and reliable. It's very similar than the model that I explained to you before, and are precipitation, actual evapotranspiration, surface runoff, and groundwater recharge. And all the elements are evaluated for a grid of 1 kilometers. This is the Big Bang computational scheme. This is the total precipitation, the actual evapotranspiration, the runoff, the recharge, and the variation, also the variation of soil water content. And then GIS calculates the balance equation directly for each cell and for each month. And you can use data also at different temporal interval. For example, you can use data for 1 year or for another year or for 6 months, as you want. The minimum is 1 kilometer and 1 month. The grid of the evapotranspiration, this, has been calculated with different methods, depending on the data availability. Where possible, Ergrave and Samani has been used, the method proposed by Ergrave and Samani from Penman-Monteir. And in other cases, the simplified Turk, as you have seen before, or Thornway, these with different methods depending on the availability of data in this area. The grids of groundwater recharge and surface resonance have been evaluated in function of the recharge coefficient, named in Italy, this acronym in Italian is CIP, and depending in function of the permeability of the outcropping rocks. And the hydrological unit map is the map published at the ISPRA website and has been transformed in this map, that is the map of the recharge coefficient. And the important availability of this data is also implemented because data can be continuously updated. And implemented with other data, for example, satellite data or other data. And you can aggregate hydrological data on different areal levels and also multiples of month time interval, quarterly, half-year, annual, etc. This is a very flexible system. And this is a proposition of use this model in other way to imagine it, to apply this to climate change scenarios, this balance. And then this is another published paper about that, the evaluation of national and regional groundwater resources under climate change scenarios. And we considered 4 scenarios defined by the IPCC in 5th assessment reports and based on representative concentration pathways. And you can see here the 4 scenarios where the first 2 scenarios, the 8.5 and the 6, are without any intervention from any anthropic intervention to reduce emissions. This is the 3 schemes of gases emissions, CO2, methane, and nitrous oxide. And this is the differences from between, beyond these scenarios. This is the worst scenario the 8.5, this is the best scenarios. And this is the differences in gas emissions. And also, we selected different time horizon where project the observed variables. For example, you use 3 future time horizons. At short term, 2020, 2039 with central year 2030. At medium time, from 2040 to 2059 with central year 2050, and long 2080 to 2099 with central year 2090. And you use for that the global circulation model solutions. Also, this solution was brought down from the web because the global climate simulation produced the United States in the National Center for Atmospheric Research, and is for the IPCC in the 5th edition is available in this format at the web, this address at the web, and use that. But what was the problem? The problem was that the grid was very large grid, is more than 100 kilometers, and then we have to downscale this data. And you used in this study, the variable used for this study are the monthly air temperature and the precipitation, both. And how downscale at local scale this data? You use the delta method. The delta method use the period of observation. The period of observation was from 1996 to 2015. And this is a historical precipitation. And then this is the base period simulated starting from the data of the global circulation model. And this is the simulated data of the global circulation model related to the projection. And this is the projection. This is the delta method applied with division for precipitation. The same method for temperature, but in this case you use the difference between the values of these and to have this projection for each year, for each interval of time. This is now the projection of the water balance components and the hydrological variables to future time horizon in Italy. Well, this is the 4 scenarios of the IPCC, and this is in column the 3 projection on time, the first 2030 at short time, at medium time, at long time. This is obviously the best projection, very similar to the historical data. And this is the worst projection, but the data for the year 2090 in the worst scenario, emission scenario, in precipitation is not so evident, but you can see the temperature is much more evident, the difference between this starting situation to arrive to this situation, to this final situation. And this is the final result of this work, of this study, because there are the projection of the annual groundwater recharge for the 4 emission scenarios and the 3 time horizon, and you can see a very big difference between this map and this map, especially in southern Italy. And then attempts to evaluate this, for example, for my region located in southern Italy. My region, a surface of 3,600 square kilometers, and is very densely inhabited because the population is 6 million of inhabitants, and is constituted prevalently by a medium part very permeable with carbonate rocks in green, a volcanic part important, this is the Vesuvio and the Phlegrean fields, and this is another old volcano, the Rocca Monfina, and this is the aquifer of volcanic materials. And in light blue, this is aquifers of coastal plains, and the gray and this the brown and this white are generally impervious material, no aquifers or small aquifers. And this is the final result with the worst scenario and the worst interval of time. And this is the observed values. There are the observed values for my region. In terms of recharge, you can see this value. For example, in carbonate aquifer, the charge is very high. You have the blues more than 500 millimeters per year. And in this scenario, values are decreasing a lot, and you have value less than 400 millimeters per year. In the southern part, the situation is critical. This is the situation for the real situation of historical data. The first projection on time, the second and the third, and this is the graph for Italy of recharge. This is in the worst scenario, the 8.5 scenario, and this is for Campania. The decrease is very high. It's very high. This confirms the negative trend assumed in previous studies. This is a study of 2008 with my colleague. It simply is just an application of my region of meteorological data, and this trend, this negative trend, is confirmed. And this is, you can see better here, where is the expression is in terms of percentage reduction of groundwater recharge in the 3 time horizon projection. You can see, and the 4 emission scenarios. And you can see that the percentage for Campania is always higher than for Italy. You can see the situation in Campania is very high. This is a terrible data. This is a reduction of the 50%. We hope that this is a not real scenario. And this is a last study with my colleagues from the University of Turin to observe the meteorological variability and the effect on groundwater quality. And this is logical. You have effect on shallow aquifer. This is a shallow aquifer in the Piedmont Plain. This is the groundwater level versus chromium. This is an anthropogenic contamination. And you can see that a very good correlation, but this is obvious in shallow aquifer. This is in Campania. The time, the interval of time observation is 20 years. And this is arsenic concentration. Arsenic is of natural origin due to presence of volcanoes in the area, is of geogenic origin, and compared with yearly infiltration. The correlation is not so good, but we a correlation. And then, and this is a deep confined aquifer or semi-confined aquifer. And then meteorological variability is an observation of meteorological variability. Climate change is a meteorological variability for other causes, but it's a meteorological variability. Meteorological variability is not sure due to climate change, but climate change sure provokes meteorological variability. And then you can expect also effects on groundwater quality. Some conclusion, some observation more than conclusion. Italy has large groundwater resources, which can also cope with drought periods because you can use groundwater carbonate aquifers of good, excellent quality. You can use these aquifers as a reservoir, and then you can overexploit these aquifers in drought periods. If you have after periods not so dry, and then you can use this aquifer as reservoir, because in Italy you have a lot of groundwater. The quantitative protection of this resource requires a deep knowledge of all the terms of the balance to, with the aim to use correctly groundwater. According to the best emission scenario, the reduction of groundwater is quite constant for all time horizon for both Italy and Campania region. But in the worst scenario, the situation is really critical for Italy and for Campania region. Ions in groundwaters are generally, hydrogeochemistry is generally strictly related to climatological data and therefore to climate change. The dependency degree is variable based on the typology of contaminant and based on the aquifer features. But ions in shallow and confined aquifers are highly correlated to the fluctuation of climate variables. While in semi-confined or confined aquifer react with a higher delay to this variation. But they react, this is important because they react with different times, but they react. And then you have consequences in long times, but we have consequences. Fortunately, we are on time to avoid severe situations as predicted by the worst scenarios. But you have to apply a sustainable management of the water resources. A sustainable management also is one topic of a future talk of this cycle of groundwater talks, I think. And finally, I will thank you. This is my town, Napoli, with my volcano. It's my volcano, Vesuvio. And thank you for your attention. If you have questions, you also can find me at my email address or now. Thank you very much.
Thank you so much, Daniela, for your presentation. It's very, very interesting in one subject of hydrogeology. So we have one question from Manuel Arias, and he asked, all the parameters that influence to get the recharge coefficient have the same way?
All the parameters that influences, sorry, the R5, no, I don't understand because it's very disturbed. Can you repeat, please?
Okay, all the parameters that they influence to get the recharge coefficient have the same way?
In what sense have the same way? I influence all the parameters. No, temperature is the parameter that influence more. In this sense, this is the question.
I will ask again to Manuel to precise the question. Give me a second.
Okay. I am here. You can see me now.
Yes. So we have another question from
Yes.
Hector Aguilera.
Thank you.
Okay, I will write in the chat. Give me a second.
I am here. Eh? The question?
Okay, I write you in the chat. Have you assessed the quality of your water balance method against, let's say, some other more complex hydrological models? This question is from Hector Aguilera.
Sorry, what is the question? About the model?
About hydrological model.
Yes, used for Italy, for the whole Italian territory. This is the question.
Yes.
Sorry, can you repeat the question?
Okay, again, I write again in the chat, in the Zoom
Yes.
chat. I don't know if you can see at this time.
Maybe it's better if I can read the chat. No.
Yes. I will share my
Yes, I think
my
it's
screen.
better.
Sorry.
Yes. Okay.
Okay, this is the first question.
The quality of your water balance, let's say more. Yes, but this is I use it in past in limited areas. This is I explain methods for big areas at national or regional scale. Are easier because you have to assess the calculation at grid scale. You need a lot of data for that. But I use a more complex model for limited areas with use Perman Montet to evaluate the evapotranspiration, or I use uncertainty method to evaluate the degree of certainty of each factor, or more than that. Yes.
We have a second question for Arif.
Is there any difference to the water balance model if you choose without transpiration? Oh, I think that yes, because Italy is, you have, for example, in my region is based on agriculture or agricultural industries, but you have a lot of cultivated and also of forests and cultivated land, and I think this is very important. And in the evaluation with the cultural coefficient in Perman Montet is very evident this, because we have a different cultural coefficient, and then you have a great variation of this parameter.
Okay, the next question is from Alejandro Jaimes.
Where can I find this investigation? Yes, there was my publication. This is apart this last that I am publishing it on water, and this accepted for publication in water. And I have other papers here. I can send him the reference, and are all, I think, available on the web, or you can, if they are not available, you can demand it on ResearchGate to me, and I can send the publications.
Okay. The next question is this.
I'm sorry, but I have no experience in tropical areas. And then I don't know which formula is better than other, because I have no experience in these areas.
Okay, the next question is from Liviu Bogdan.
How long was the period of data used in your simulation? In the simulation, the observation data is from 1996 to 2015, but this period is to have homogeneous data. You can have a continuous observation from 1950 to now, until now, but the levels are different, the stations are different, and hence it's not so correct to compare that. But the interval used in the study is from 1996 to 2015.
Okay, the next question is from Manuel Arias.
Yes. Is necessary to consider other qualitative factors to calculate the recharge, like lineament, slope, and geology? Well, it depends, because lineaments, the coefficient of recharge is changing with lineaments. If you have a lot of faults or tectonical active area, you have different data for that. And then any kind of data, you have to test, I think, this kind of data in your area to see what effect on permeability have these factors.
Okay, the next question is from Hector Aguilera.
Does the method provide confident intervals of the, I don't understand, please, this demand. This question, does the method provide confident intervals of the water balance figures? Figures in what kind of a sense?
We need to precise a little more. So the final question from Liz Balbuena.
What tools or satellite technology do you recommend to obtain meteorological data? To obtain meteorological data, you have in Malaga at the Edge Congress this year, I saw a very good presentation to evaluate directly recharge from satellite data. But it depends. If you have a shallow aquifer, you can do that. But if you have a more complex aquifers, I think it's not so easy. For meteorological data, for temperature are okay, satellite data depends on, for the news are perfect, clear. Depends on the parameter, it's not fixed. It depends on the situation that you have, the local situation.
We have a final question from Hector Aguilera.
Ok, dunque. This the method provide confident interval of the water, but like an estimation error. Yes, you have to, this is an important, this is the calibration of, I think, of these models, and it's an important phase, I think. But I think that they did this evaluation, but I have no data about that. But I think that this is important. It's an important phase of this kind of models.
Okay, thank you so much, Daniela, for your presentation and your wonderful subject. And everyone, I put a little link in the chat to for everyone to know what is your experience about this conference. And for tomorrow, we have a new conference from the Netherlands president. Yes, okay. From the Niels Hartog, from the Netherlands IAH, president of national chapter. And see you at the same time. Thank you so much, Daniela, again. And you are welcome to join for the next webinars as well.
Thank you very much. Bye. Bye. Bye.